Welcome back to the Professor's DuBois channel. Today we're going to continue our lecture series for General Chemistry 1, and today we're going to talk about a class of compounds called hydrates. And we'll get into what those are, but we're also going to talk about how to calculate and determine the formula of these hydrates. So let's get going. Ready?
Sure.
All right.
Okay, so what is a hydrate? You know, when I heard you say we're going to talk about hydrates, I started getting thirsty, and it really doesn't have anything to do with thirst, but it does have something to do with water. So salts, the term salt is really, and I don't know if we've talked about this before, but an ionic compound is a salt. So we're used to table salt, which is sodium chloride, which is an ionic compound, but any ionic compound is a salt. Now, we also talked about how ionic compounds form these large three-dimensional crystal lattice type structures. Well, certain salts, when they form these structures, have like openings that are large enough to trap molecules of water. And what's really interesting is that each of these openings will have the same number of water molecules trapped inside of it.
And we call these waters of crystallization. And you might also hear that there's a water of hydration, and it's really just the number or the ratio of how many waters there are to each salt. So how do we represent that with a formula? In this first example, we have BaCl2, that's barium chloride, dot 2H2O. And this formula, the entire thing is the formula for that hydrate. And that means that we have two water molecules trapped within the crystal lattice for every BaCl2. And this is a mole-mole ratio. So we have two examples here of hydrates. And when you name these hydrates, you're going to use your same prefixes that you use for your naming of covalent compounds. So we have two waters for this compound, so it's a dihydrate. So we say barium chloride, just the name of the salt, dihydrate. And for the other example, it's 7, so that's hepta. So magnesium sulfate, heptahydrate.
So these water molecules are in defined ratios, meaning that for a particular compound, there's going to be a certain number of water molecules. So this barium chloride example has the 2H2O, so that's saying for every one barium chloride, we have 2 waters. And this just unlocks a whole bunch of mole-mole ratios. So we've kind of got the mole-mole ratios in red here. So I can say for every one barium chloride dihydrate, there are 2 waters. For every one barium chloride dihydrate, there's 1 barium. For every one barium chloride dihydrate, there's 4 hydrogens, and so on. We can break it down even more. You see here we've got for every 1 barium, there's 2 chlorides.
Yeah, so you can see why I wanted you to do this slide.
Yeah, that was a mouthful.
Yeah, there's a lot of mole-mole ratios, and they're not even all here. So you can see how that works. All right, so finding the formula. So here's our calculation piece. We want to know what is the formula for these hydrated compounds given some data. So if we heat these hydrates, we can drive off that water. We can evaporate or vaporize the water molecules that are trapped within the crystal. So if we start with a hydrate and heat it and continue to heat it until the mass is constant, we've driven all of the water off. So we can have our initial mass, and in this question we have an initial mass of 1.023 grams of this salt, of this hydrate, and after it's been heated and the water is lost, this is how much remains. So we need to determine a formula, and a formula means we need to know what that mole-mole ratio is, how many waters for each salt. So if we need moles, then if we need the mole-mole ratio, we need to get to moles, and the way we're going to get to moles is from grams. We know what the hydrate salt is. It tells us that it's a copper 2 sulfate salt. And we know how many grams of the hydrate we started with and how many grams remain. So this 0.654 grams is the dry mass of just copper 2 sulfate. So we can start with the grams of that and get to the moles. So the remaining grams of the salt is the dry mass. We can convert that to moles. The grams of water is the difference between these two, because this is the dry mass. If we started with something wet and dried it, the difference was the water that was lost. So we have the grams of water, we can convert that to moles, and then we have a mole-mole ratio. And I'm going to show you a trick on how to, actually, we already taught you that with dividing by the smallest one. Will get you one of those moles will turn into at least one whole number, which is 1, and we need that whole ratio of moles to get to that formula. So let's show you how this is done.
And some terminology you might see are words like dehydrated, and that means that it's dry. So notice here it says find the formula of hydrated. That tells us that we have a hydrate. We just don't know how many waters are there. So you might see terms like dehydrated, meaning that's the dry, that's the 0.654. Another word you might see is anhydrous, which means dry,
without
essentially.
Water.
And what's interesting is these solids, they're not wet, even though there's water molecules trapped within the crystal. They're crystalline materials, and they're actually dry. Anyway, we know how many grams of the anhydrous, the dehydrated, the dry copper sulfate we have. We get the molar mass from our periodic table, and we can go from grams to moles. Likewise, we can determine how much water there was by taking the difference. We had the starting mass, and with the mass that remained, the difference is the mass of water that was lost. Using the molar mass of water, again from the periodic table, we can convert that mass, 0.369 grams, to moles. Now we have the mole-mole ratio, but these aren't whole numbers. So the way we can get to whole numbers is to divide both of those by the smallest one. The smallest one here is the 0.00410. So if I divide that by itself, I just get 1. So I'm going to have 1 copper sulfate. Now if I take the moles of water and divide by the 0.00410, the smallest one, I get a number that's pretty darn close to 5. And so that is copper 2 sulfate pentahydrate.
Nice. So here's another example. Find the formula of hydrated cobalt 2 chloride if, after heating this many, so this is what we're starting with, this is how much remains. So this is the dry mass.
Or anhydrous, or dehydrated.
And this is the hydrate. So we need to start with, so we know we have this many grams of dry salt. That's really important, and this is often an issue that people start. They don't really know which one to convert into their salt moles, and that's the dry salt. You need to use that. And then we also have a subtraction. So if we subtract the hydrated, or subtract the dry from the hydrated, we get the grams of water lost. If we have grams of the salt and grams of the water, we can convert to moles and divide by the smallest one, get our mole-mole ratio. So here it is all worked out. We start with our mass of our dry. Remember, this is our dry stuff. This is our anhydrous or our dehydrated. This is from the periodic table. Okay, we were told that it was cobalt 2 chloride. You need to be able to convert that into the formula of CoCl2 from your name. From that, you can use the periodic table to get the molar mass and convert to moles. Again, we have the subtraction to get the amount of water that was lost, and we can convert grams of water into moles of water. We can't use these decimals as our mole-mole ratio. It is a mole-mole ratio, but we need to represent our formulas in whole number ratios. So we divide both by the smallest one. This is our smallest one. If we divide it by itself, we get 1. If we divide the other one by the smallest one, we get 6. So that means we have 6 molecules of water trapped in the crystal lattice of that salt for every 1 CoCl2. So our formula is that.
And that would be called cobalt 2 chloride hexahydrate. The hexa for the 6.
Nice.
This is a really tricky question. So we can actually go in the other direction, meaning that we can have the formula. We know that this is 10 waters. That's a decahydrate. And if we had 100 grams of that and we heated it to a constant dry mass, we can figure out what the mass of the water in that is. So it's kind of working backwards. So if we use the molar mass of the entire hydrate, so that's the sodium carbonate and the 10 waters. So we're gonna use our periodic table and add all of those up. Then we'll have the molar mass. We can use the mole ratio. Well, we'd take our 100 grams and go to moles. Then we can use the mole ratio to figure out how many moles of water there are, and then we can go from moles of water to grams of water using the molar mass of water. And it's just kind of like working in reverse, a little bit tricky.
But it comes back to that same compound stoichiometry, right? So we have this formula and we have mole-mole ratios within it. So if you know the moles of one piece and you have the mole-mole ratio, you can get the moles of the other piece. So we have the mass of the entire thing, we can get moles, and our mole-mole ratio is this 10 to 1 ratio. So let's give this a go. So if we start with 100 grams, this is from the periodic table, and that includes the 10 waters. You have to add 18 grams for each water, so that's times 10. So it's a pretty large molar mass, grams per mole. Now we have the moles of the entire hydrate, and this is the mole island piece. This is the compound stoichiometry piece. There are 10 waters for every 1 hydrate. So that means there's 10 moles of water for every 1 mole of hydrate. That means we have our moles of water, and easy peasy, from moles of water we can get grams of water from the molar mass.
All right, this is where you want to pause the video, jot these down, try to work through them. We're going to give you the answers in just a few seconds. So we've got some questions here, including one where we have to work kind of backwards, it looks like.
Yep.
And I just want to point out milligrams there in that last question. That's a little tricky. We're used to going to grams. You're gonna have to convert your result to milligrams there using that conversion.
Nice. Yeah, so practice, practice, practice. We are all about giving you lots of practice to do. So here are your answers.
All right, hopefully that's what you got. That CONO32, that 2 should be subscript.
Oops.
Like the one
Look at
below,
that.
but
I was supposed to fix that. That was my fault. There it is.
so we've got a copper 2 nitrate, trihydrate, and I don't know what the 12 is. Is that like dodeca or
it's
something?
dodeca.
It's dodeca.
It is.
Okay,
Yeah.
so that's a potassium aluminum sulfate dodecahydrate. Holy moly.
AKA alum.
Alum.
Thanks for watching.
All right, thanks for tuning in, you guys.
Catch you in the next one.